Cool. All right, so we got to finish off our discussion of these Diels-Alder reactions. Just a reminder, these reactions take place between our conjugated dienes and what we call a dienophile. Up until this point, we just said our dienophile needs to contain a pi bond, and we create these 6-membered rings in our Diels-Alder reactions. 4 of our carbons come from our conjugated diene, the other 2 from our dienophile. That's how we get that total of 6 carbons in our ring. We also have this movement of our pi bond in the 6-membered ring that we create. So we create a cyclohexene ring here, all right? We need to talk a little bit more about these dienes and these dienophiles, specifically what would be good for these Diels-Alder reactions. Because if you take this molecule here, 1,3-butadiene, and ethene here, you can get a Diels-Alder reaction to happen, but the yield is complete crap and you have to crank up the temperature to like 200 degrees. It's just not very favorable if you pick just any old diene and any old dienophile, all right? So we have ways of activating these reactants to make them even more reactive in a Diels-Alder reaction, okay? So that's what we're gonna cover now. Okay, first, we're going to talk about our dienophiles. If we want to make them even better dienophiles, we can activate them with what we call an electron withdrawing group. All right, and we're going to see this concept of an electron withdrawing group come up again in this semester here. All right, this is a functional group that we're going to tack on to this molecule that's going to withdraw or pull electrons away from that dienophile. Okay, so let's just take our dienophile here. We'll even keep it in our same orientation that we like to see for our Diels-Alder reactions. And I'm going to tack on this electron withdrawing group. What do we call these bonds? Carbon-oxygen double bonds. What are they? Carbonyls. All right, so a carbonyl is a classic example of an electron withdrawing group. Not only do I have a carbonyl group on this molecule, but what could we say about that carbonyl group with this spacing of double bond, single bond, double bond? What would we say? It's conjugated, right? So this carbonyl group is conjugated to my pi bond here. Okay, so this is what we call an electron withdrawing group, and what we're going to do is we're going to demonstrate that electron withdrawing by putting in our resonance structures here. Okay, let's remember that this carbonyl group was one of our resonance patterns, a pi bond between 2 atoms of differing electronegativity. That more electronegative atom can pull that pi bond onto itself. All right, so everybody's going to take a second and draw me my next resonance contributor here. Okay, we worked on following our electron pushing arrows last week. All right, so this arrow here was what? Bond breaking, bond formation, bond breaking. So this pair of electrons that was bonding is going to turn into a lone pair. So now we got a lone pair sitting on that oxygen, meaning it has to have that negative formal charge. So then what else must be missing from this molecule? The positive charge, right? Everything's got to be neutral since my first structure was neutral. And importantly, it might be a little hard to see because we don't have our implied hydrogens drawn in there, but this carbon got that pair of electrons taken away from it, so it's left with this positive charge. And we can draw yet another resonance structure here because this is another one of our resonance patterns, an allylic carbocation. All right, so again, just following our electron pushing arrows here. Everybody take a second. This pair of electrons in my pi bond, gonna jump over All right, so now we have this. Importantly, this arrow here is a bond breaking / bond formation arrow. That double bond flips to the other side. So now my double bond's located here, and my carbocation has moved to the very end here. Okay? Now, since these are resonance structures, we're going to be good, and we're going to put these in brackets to remind ourselves that it's not like one of these structures is true at any given time. It's that all three of them are true together. Okay? And importantly, what this shows is that certain carbons, and the one that's very important because it's involved in our Diels-Alder reaction is this one down here on the end, lacks electron density compared to what you would expect in a normal pi bond, right? That's what our resonance structure here is showing. And I just want to take a second to, again, emphasize we called this an electron withdrawing group. So we all just want to take a step back and convince ourselves that this carbonyl group indeed withdrew electrons, pulled electron density away from that carbon-carbon double bond and onto itself, right? That's why we were left with this positive charge down here. So again, since all these structures are true at the same time, we just want to note that this carbon at the end here, one of the ones that are involved in our Diels-Alder reaction, lacks electron density. That's what our resonance structures are showing here. Cool. So we can activate a dienophile with an electron withdrawing group. All right. Similarly, for our conjugated diene, okay, we can activate that with an electron donating group. Okay. Our electron donating group here. We're going to sort of have an easy pattern to spy here for our electron donating group. These have an allylic lone pair. All right, so let's take our diene, our conjugated diene. I'm even going to keep it in that same orientation we like for our Diels-Alder reactions. And I'm going to now stick on there an electron donating group. Again, I need an allylic lone pair. So I'm going to put an oxygen. Oxygen has an allylic lone pair. I could have used nitrogen as well, one of my heteroatoms that have a lone pair. That is really ugly. I have to fix that. Okay. Cool. And whereas my other group was electron withdrawing, this group here is going to donate a pair of electrons to that conjugated pi bond system. Okay. Now I can't stop there or I'd break that carbon's octet rule. So remember with our allylic lone pairs, we had these 2 electron pushing arrows that we had to draw in for our resonance. So everybody's going to take a second and draw me my resonance contributor that we just sort of led to here with our electron pushing arrows. All right, so that first arrow was what? Bond breaking or bond formation here? Bond formation. And since now my oxygen has 3 bonds and only 1 lone pair, it needs positive formal charge. Okay. And what about this one? Bond breaking or bond formation? Breaking. So this pair of electrons is going to become what? A lone pair. And again, I have this allylic carbocation, or this allylic lone pair here, same resonance pattern as we saw before. So again, we can do one more resonance jump here. This is going to come down here, This is going to jump over here onto this carbon. Put it on the other side. And so again, let's do our last resonance structure. Cool. So now our bond has moved, and we have a carbanion down on that last carbon. And again, we're going to put these in our brackets to remind ourselves that they're all true at the same time. And importantly, what our resonance structure showed here, what our resonance structures show, is that that pi bond electron distribution is not evenly distributed between these carbon atoms, but there are certain carbons, this one here and this one here, that have more electron density than you would expect, right? That's what our resonance structures are demonstrating. Because of this electron donating group, we got certain carbons that have higher electron density than what we would have without that electron donating group. Cool. All right, so bottom line is we can make these our reactants more reactive in a Diels-Alder reaction by taking our dienophile and adding an electron withdrawing group, or if we took our diene and added an electron donating group. These make these more reactive. We get a better yield at lower temperatures in a Diels-Alder reaction if we stick these types of functional groups on our reactants in these Diels-Alders. Okay? One more thing that we're going to take this opportunity to introduce, one new functional group, it's got a pretty cool name, is a nitro group. All right, this is a new functional group that we'll see come up a few times this semester. And what we want to note about our nitro group is that it is a strong electron withdrawing group. All right, so carbonyl bonds are good electron withdrawing groups, as we showed in this example. A nitro group is yet another electron withdrawing group, so it can be used to activate our dienophile. All right, a nitro group you will see abbreviated as just simply NO2. All right, but we're going to draw out the full full Lewis structure here for our nitro group, so we can see why it's such a good electron withdrawing group. All right, and again, I'm going to kind of use this as an opportunity to make you practice first semester material here. I want you to take this nitro group here, and you're going to fill in any missing lone pairs and formal charges. All right, what does this oxygen need? 2 lone pairs. What does my nitrogen need? Positive, yeah. So we got 1, 2, 3, 4 bonds with our nitrogen, meaning it's already got a complete octet, so no lone pairs. It needs that positive formal charge. And what about our single bonded oxygen? 3 lone pairs to complete its octet, which means it's got negative formal charge. Okay, so just like a carbonyl group, this thing can accept pairs of electrons by kicking that pi bond up onto that oxygen, right? So another electron withdrawing group. Okay, so again, just like our other electron withdrawing group, it can be used to activate a dienophile. Cool. All right, so now we got to take these activated reactants here And we're going to do our Diels-Alder reaction. All right, but now with our activated reactants. Okay, and up until now, all of our Diels-Alder reactions that we've been doing had either a symmetric diene or a symmetric dienophile, meaning it didn't matter which way you aligned these up. You'd always only get just one product on the other side. Well, now because we have that functional group on there, these are no longer these symmetric molecules. So it's going to matter the direction in which I line it up. I could get two possible different products, all right? And what we're going to see is we have to deal with our regioselectivity of these reactions. All right, by our regioselectivity, we mean that we get one preferred orientation of our reactants. All right, so I want to kind of make this a little bit more straightforward as to how we're going to go about this. So I'm going to sort of break this into steps. Step one, we're going to line up our diene and our dienophile for a Diels-Alder reaction. All right, let me just make this a different color. Okay, so by that, I mean, just like we were doing before, we're going to take our, and we'll use the ones that we did in our example previously. So we're going to take our conjugated diene with that electron donating group on it. And we're going to line it up in this way that we like to do for our Diels-Alder reaction that makes it a little easier to see that six-membered ring that's formed here. So here's my diene with the OH group. Here's my dienophile with that carbonyl bond. And they're lined up side by side where we can see how that six-membered ring is going to be formed. All right, so for the sake of practice, everybody's going to take a second and draw me my product here. All right, given this particular orientation, close that ring, give me my Diels-Alder. All right, what do we start with? What's always formed, right? That six-membered ring. All right, and why do we get a six-membered ring? Because we have our 4 carbons in our conjugated diene and our 2 carbons from our dienophile that make up our ring, right? All right, now I'm going to make sure I got to decorate these with these functional groups here. So on that first green carbon, I need my OH group. And on that first purple carbon, I need that aldehyde group, right, my carbonyl. Okay, and the last thing that we're missing here for our Diels-Alder would be what? That double bond, right? So that double bond that moved between carbons 2 and 3 in our diene. Okay, I'm going to get rid of my little markings here because I'm going to prove a point later, but that's helpful to see how that ring forms in the first place. Cool. All right, but again, these molecules here are not symmetric. So I would get a different product if they had aligned themselves up in a different orientation. So what I'm going to do now, I just picked a random one to start out with, but now I'm going to take one of my two reactants. I'm going to say, let's pick our dienophile. It doesn't matter which one you picked, but we're going to pick one of them, and we're going to flip it upside down. All right, we need it to be in the other orientation here. So now we're going to line up, but we're going to flip. That's not how you spell that. We'll flip our dienophile like a pancake. Meaning, I want you to imagine that I have a spatula and I put it under that molecule and I flip it over like a pancake. Now, I still want that double bond aligned. So again, we're going to keep one of these the same. But now my dienophile, I'm going to point in the opposite direction. So now that carbonyl bond is not pointed up, it's pointed down. All right, and now you're going to take me with this orientation, take me to my Diels-Alder product. All right, so I get the same six-membered ring. It's got the same two functional groups, but now those functional groups are spaced apart differently. All right, so depending on which way I orient my diene and my dienophile, I get two different possible products. Okay, let's call this one up top here. This one we're going to call our 1,2 product, since they're 1,2 carbons apart on that ring. And this one we're going to call our 1,3 product, since they're 3 carbons apart on that ring. So again, we get two different molecules depending on which way we orient this. If a Diels-Alder reaction was not regioselective, then we would just get a 50-50 mix of both of them, right? If it didn't matter which way we lined it up, we would get even number of 1,2 and 1,3. It'd just be random chance, okay? But it turns out that in a Diels-Alder reaction, it is regioselective, so we only get one of these two products in this reaction. The other one doesn't form, all right? So which one forms and why? All right, so let's just ask ourselves, which product forms and why? All right, so we're going to address the why first, because this is how we're going to understand why this reaction is regioselective. All right, and the why is simply because of those resonance structures that we drew. right, so the way that we're going to understand which one of these two products forms is we got to go back to those resonance structures and what they were showing about the relative electron withdrawing or electron donating of those two reactants. Remember, in our dienophile, we had this electron withdrawing group, and that left this carbon on the end with a relative lack of electron density, right? We had this positive charge in one of our resonance structures indicating that we don't have a lot of electron density on that particular carbon, all right? So we can draw it in with our resonance structures, but I'm just going to actually highlight it here like I did on this structure. We're going to note that this carbon right here has low electron density. Let's actually just give it a partial positive charge. All right, if I did the same thing on my other orientation, it would be this carbon here, the one at the end again, that has that partial positive charge. All right, if I play the same game with my diene, what did we show with our diene? Do those carbons that I have colored in red here have a lack of electron density or a lot of electron density? A lot of it, right? They have these negative charges according to my resonance structures. So we're going to go through and we're going to mark. These ones have a lot of electron density or have a partial negative charge. Okay, so which one of these two orientations is going to be more favorable? We have one here where our positive charge and our negative charge are right next to each other. Our partial positive and our partial negative charge are right next to each other. Or one where they're catty corner to one another. What do we think will be more favorable here? Do positive charges want to be next to negative charges, or do they want to be far away? No, they want to be close. They're opposites. They attract, right? Not only that, but let's remember what's going to happen in this reaction is our electrons are going to move in a circle. Well, if this carbon right here has a relative lack of electron density, that means it's going to want to accept that pair of electrons even more, right? So, turns out that our 1,2 product is going to be our preferred product. It's going to be the product that forms here. And our 1,3 product does not form. Okay, so because of our resonance structures, a partial positive charge, partial positive carbon, let's just use our delta symbol. I lied. Let's say our partial negative carbon wants to donate electrons to a partial positive carbon next door. All right, and which of our two products formed what we called our 1,2 product here, right? We don't get our 1,3 that forms. So product that forms, our 1,2. This is a convenient thing to keep in mind because since we always activate a dienophile with an electron withdrawing group, and we always activate a diene with an electron donating group, you always have these same resonance patterns. So it's not like sometimes we would get a 1,3 depending on what our functional groups are. They're always doing the same in terms of our resonance patterns, right? This one's necessarily donating electrons, so that will lead to a negative charge or a partial negative charge on those two carbons. And this one's withdrawing electrons, which will lead to a partial positive charge on that carbon. Okay, so we can just kind of simplify this down to this rule of drawing our 1,2 product. However, you do want to make sure that you can explain to me why using those resonance structures. Okay, I am going to leave to you one other situation. All right, so this is for you to do. Okay, you need to draw the possible resonance structures. Okay, for our dienophile, there really wasn't another way that I could have stuck that electron withdrawing group on there. But for our conjugated diene, I could move my electron donating group over 1 carbon. And in order to figure out what our product's going to be, what those preferred orientations are going to be, you're going to have to draw these missing resonance structures, line them up in that preferred orientation where your partial negative carbon is next door to that partial positive carbon. All right? So again, this one I'm going to leave for you all to do, making sure that we understand the logic of what we just did above. All right, so yes, this is for you to fill out. Cool. All right, because we're going to switch gears now. We're going to talk about our last reaction of our conjugated dienes here. This is what's called an electrophilic addition. To our conjugated dienes. Okay, and I know everybody was immediately like, man, I remember exactly this that we did because we did this last semester. So let's just review when we talked about electrophilic addition to just regular old alkenes. All right, and I legit think that there's a good chance that you do remember this because this is one that we kind of beat to death here. We're going to take an alkene. We're going to react it with an electrophile, and specifically we're going to use our hydrohalogens, or what we call a hydrohalogenation. Okay. So, given what we discussed maybe even 2 weeks ago when we were reviewing nucleophiles and electrophiles, which one of these would be the nucleophile in this reaction? The double bond. Somebody said it. All right. Yeah, our pi bond. All right. So our pi bond plays the role of the nucleophile. This is an acid, so it's our electrophile. Specifically, what's the electrophilic site? The hydrogen. All right. So our first step here is our nucleophile attacks our electrophile, kicking off that bromide ion. Okay, so this was just a bond breaking arrow here. So now I have a bromine that has 4 lone pairs, which means it should have what? Negative charge, which means that my organic intermediate here better have a positive charge. Okay. And this was our first little dabble into regioselectivity here, because we could have 2 possible carbocations that form. Okay. Which one of these is going to be my intermediate? The one on the left or the one on the right? the one on the left. Why is that? The more stable carbocation, because it's the more substituted carbon. All right, cool. So we're just going to get rid of this. This one doesn't form. Everybody's going to take a second, and actually we should be good and make this reversible, that first step. And you're going to take a second and finish off this reaction for me. What would my product be? Put in those missing electron pushing arrows. Draw me my product. All right, my bromide is now my nucleophile attacking that great electrophile, that carbocation, leading me to my addition product. I have a hydrogen added to one carbon and a bromine added to the other carbon. Cool. And again, this is our intermediate. We have this regioselectivity because we have the more stable carbocation that forms. So let's just remind ourselves here, we built this whole ranking of carbocation stability. Okay, we're going to do the same thing where we're going to rank these from the least stable to the most stable. Our least stable carbocation is what we call a methyl carbocation, where it's got no carbon neighbors. All right, and our trend here was that we simply increased instability as our degree of substitution increased. So next was primary, then secondary, then tertiary. All right, and I'm leaving some room over here because I'm going to complicate things a little bit. Cool. So we said our degree of stability of our carbocations, it simply trends with degree of substitution. How many carbon neighbors that carbocation has. No carbon neighbors is going to be the least. One carbon neighbor is next. 2 carbon neighbors is next. And then if we have 3, that's the best. Okay? Cool. So now we did our, and that explained why our carbocation formed over here as opposed to over here. All right, but now we're not talking about just regular old alkenes. We're talking about our conjugated dienes. I'm just going to steal this same header. All right, so rather than propene, I'm going to use 1,3-butadiene here. Our smallest possible conjugated diene. All right, well now what do we think our nucleophile is going to be? What is it? Still the pi bond. All right, nothing crazy. All right, we still have our pi bond and our strong acid. So our pi bond is going to be our nucleophile. our acid is going to be our electrophile, specifically at that donatable proton. Okay. Where is my carbocation going to go? On the orange carbon or on the green carbon? Orange carbon, and why is that? So more stable, okay? But there's something even more important than degree of substitution that is going to indicate this, which is what? Resonance, which is because it's in that allylic position. Remember, we said there's something even better than being a tertiary carbocation, and that is when we're a carbocation that's right next door to a carbon-carbon double bond because it's stabilized through resonance, right? What we call an allylic carbocation. So in this particular example, it does happen to be both allylic and more substituted, but we're going to make a note here that this is a big difference between what we saw with alkenes and what we saw with our conjugated dienes. All right? We're going to always get an allylic carbocation intermediate. All right, my bromide ion right here. Okay. What's going to be the nucleophile in this next step? Still the bromide ion. What's going to be my electrophile? Still the carbocation. All right, so boop. All right. So we're going to brominate that allylic position there because of our allylic carbocation. All right. So far, nothing crazy. Correct? Pretty much exactly copy and paste of what we just did, with this notable exception that we're going to make sure to always form an allylic carbocation, and we still have one of those double bonds of the two that we started out with in our product. All right? Now, I know everybody's been waiting for the twist because it's not going to be that easy, right? So what is that twist? All right? So importantly here, we said that this carbocation forms in the allylic position because it's resonance stabilized. So that means that we can undergo resonance here of that allylic carbocation. And I'm going to use blue arrows here to make this more apparent. But remember, with our resonance patterns, what's going to happen? That pi bond and that carbocation are going to swap places. All right, so because of that allylic position and that resonance stabilization, my carbocation is kind of bouncing between those two carbons, which means that my bromide ion can not only attack that original position, but it can also attack my new resonance position. And this would lead me to a different product. All right, actually, I'm going to put in my implied hydrogens here to make a point. Make some room. Okay, importantly, because my carbocation formed in that allylic position, the position of the hydrogen doesn't change. That was always added on to that first carbon, right? But now I have my bromine added on to a different position, all right? We call this first product our normal old nothing special product that we would expect just based on what we learned about electrophilic addition to alkenes. We call this the 1,2 adduct because the hydrogen and the bromine are added 1,2 carbons apart, and an adduct because it's an addition product. So this is our 1,2 adduct. All right, our other product we call our 1,4 adduct because the hydrogen was added 1, 2, 3, 4 carbons away from the bromine. All right, so for our 1,2 adduct, let's just note this is kind of just our normal addition product. Literally nothing special compared to what we learned previously. All right, but that 1,4 adduct, we're going to note, is a result of the resonance of that allylic carbocation. All right, and then just playing like spy the difference game. Obviously, the hydrogen and the bromine are located different number of carbons apart. What else is different about the 1,4 than the 1,2? The pi bond has moved as well, right? So let's just note, because it's due to resonance, we get our pi bond moves. All right, moves between carbons 2 and 3 in our product. Cool? All right, so first of all, nothing too terribly crazy different about our nucleophile and our electrophile. Our nucleophile is still going to be that pi bond. Our electrophile is that strong acid, that hydrobromic acid. But we've created this allylic carbocation, and allylic carbocations can undergo resonance, which is why we have these two possible addition products here. What's up?
Would it want to be in the one with the pi bond where it's like not the terminal one?
Cool. So we're going to talk about, right now, let's just make sure that we can wrap our heads around the fact that we could get two different products. And then we'll talk about which one is preferred here in a second, all right? But right now, let's just note that we can get, because of resonance of an allylic carbocation, we can get these two possible products, all right? So what I'm going to do is I'm going to summarize this in a balanced chemical equation. Okay. Or I guess just a chemical equation here. We treat a conjugated diene with hydrobromic acid, and we get these two possible products, our 1,2 adduct and our 1,4 adduct. Okay, now You're exactly right. That we're going to be paying attention to position of double bond, all that jazz. It turns out that it's even a little bit more complicated than that. We can tune this reaction to go towards one product as our major product or the other one as our major product by varying the temperature of our reaction here. All right? It turns out that at low temperatures, our major product is this 1,2 adduct. And our minor product is the 1,4. All right, but if we crank up the heat, we do this same reaction at high temperatures. Now our 1,2 is our minor product, and our 1,4 is our major product. All right, so we can tune this reaction to give us one product over the other depending on the temperature. All right, this reaction in terms of our product distribution is going to depend on the temperature that that reaction is carried out. All right, we're going to make a note here before we move on that this here is going to depend on your diene substrate. So this particular distribution is true for the 1,3-butadiene that I'm illustrating here. But in general, where we're going here is we're going to have to pay close attention to our diene in order to figure out what this distribution is. Okay, so I just don't want us to get too married to this chart like it's always true. It's true for this particular substrate. What we're going to learn is what to look out for in terms of what these distributions are. Okay, let's first try to understand why this is true for our 1,3-butadiene. All right, and to do that, we're going to turn to our energy diagrams. And we're going to note that this is specific for the 1,3-butadiene. All right, or we can say electrophilic addition too. Okay, what do I mean by energy diagram? So we're going to make this graph. Where on the y-axis we have energy, and on the x-axis we have reaction coordinates. Okay, I'm going to have to draw two different curves here. I'm going to use different colors for our different products. So first of all, let's just real quick, everybody, when I'm talking about my energy diagrams here, I'm talking about these sort of curves that look like this, right? We remember these? Remember that looking at the endpoints, we get some information about the thermodynamics of the reaction, how favorable it is from an energy standpoint. And what do we get by looking at the middle? Activation energy, which corresponds to what? Starts with a K. Kinetics, how fast or slow the reaction is, right? So those are these pieces of information that we get from our energy diagrams here. Okay. So first, I'm going to do the 1,2 adduct in blue. All right, and then I'll do the 1,4 in red. Okay, so we're going to start over here. Okay, our energy diagram for this reaction would look something like this. Okay? Remember, our reactants live over here. Our products, and so specifically this would be my 1,2 product, lives over here on this side. And what's in the middle here? Our intermediate, yeah, okay. And what's this little hump here for? What lives in there? What's our intermediate in this reaction? Our carbocation, right? So the reactant gets converted to a carbocation, then our carbocation gets converted to product. That's what our free energy diagram here is showing. Cool. All right, so now we're going to put in our other energy diagram. And importantly, our reactants are the exact same. So we're going to start off at that exact same energy level. All right. Furthermore, that very first step is forming that same carbocation. So we also go to that same level there. All right. But that next step that happens has a higher activation energy than our 1,2. All right. So let's just note here that our blue curve has, and I guess just to be clear here, right? Remember, our activation energy is the distance from here to the top of that hump. So our blue curve has a lower activation energy. Our red curve here has a higher activation energy. So let's just note 1,2, lower activation energy. All right, but our red curve here continues to fall just like the blue curve, but it will actually finish out at a lower energy level than the blue curve. All right, remember the red curve represents our 1,4 product. All right, so we just want to note that whereas our 1,2 has a lower activation energy, our 1,4 has a lower final energy. Or product energy, maybe we should say. Okay, so before we talk about why this is, let's just make sure that we can tie this into what we talked about up here, about what was major and what was minor at these different temperatures. Okay, so first of all, if the 1,2 has a lower activation energy, what does that mean in terms of kinetics? It forms faster or slower than the 1,4? Faster, right? Remember, our little, we think of our reactants as this little ball. It's got to jump over this activation energy barrier. The lower the activation energy, the faster that will form. Okay? Well, what do reactants use to jump over activation energy barriers? What do they need? Catalysts would be great. We don't have any catalysts here, right? And catalysts would just lower that activation energy barrier altogether, right? But what do reactants, what energy do they use to jump over stuff? Heat, okay? So if we're at low temperatures, this thing does not have enough energy to jump over that high activation barrier. It can only go over the little one here. So that's why at low temperatures, our 1,2 product is our major product. We don't have enough energy to do very much jumping at all, okay? So then why at high temperatures is my 1,4 favored? Well, now I have enough energy to jump over anything I want. I can jump over this one, I can jump over this one, and I'm going to want to go to the lowest possible energy level here, right? So at high temperatures, we have plenty of energy to jump over that larger barrier and get to that more desirable lower energy final product, all right? This is something that we're going to see a lot in our organic chemistry, our second semester here, what we call this kinetic versus thermodynamic product. One of these products is more kinetically favorable. It's got a lower activation energy. That would be our 1,2 product. But the other one is more thermodynamically favorable. My product energy level is lower. All right? So we're going to make some notes here. We have what we call our kinetic product. This is the one that's favored at low temperatures. All right, I'm going to leave a room for a bunch of notes here. I'm going to go about like halfway down the page here, and this is going to be our thermodynamic product. Which we get at high temperatures. Okay, so our kinetic product, what we mean by that is our product that forms the fastest. All right, and as we said, why does it form the fastest according to our free energy diagram here? Because it's got the lower activation energy barrier. All right, so our kinetic product, the one that forms the fastest, is the one with the lowest activation energy. Okay, whereas our thermodynamic product, this is the one that is the most stable product. All right, and according to our free energy diagram, why is it the most stable? Because it's got the lowest final energy. Okay, so why then is our 1,2 the kinetic product and our 1,4 the thermodynamic product? Why would the 1,2 form faster but the 1,4 be more stable? Okay, so the 1,2 here, it's, remember, let's just go back to our diagram actually. Our 1,2 we said had a lower activate, both form that carbocation, but the 1,2's got a lower second step than the 1,4. So why is that? All right. Remember that our 1,4 product was the one that formed via resonance. Okay. But resonance is not a slow event. Resonance is almost instantaneous. Remember, both of these structures are true like at the exact same time. So it's not like this step right here is actually what the slow part is. This is a little bit counterintuitive, or at least not so easy to wrap your head around as to why this step here would be so much faster than this step here. But it doesn't have to do with the allylic carbocation. It has to do with that bromide ion. All right? Remember that these reactions, we talk about this in Chem 1B, the reason why reaction happened is because two reactants collide with one another. Right? So these two reactants have collided with one another, forming that carbocation on one carbon and my hydrogen over here. Well, where is the location of that bromide ion relative to that carbocation? When that carbocation forms, that bromide ion is right next to it, right next door. And if that bromide ion wanted to move all the way to the other end of the molecule, it would need thermal energy to do it. It would need to be moving because of heat. And if we're at really low temperatures, this bromide ion is not booking it over to this side of the molecule. It's chilling right here directly next to that carbocation. So this one forms the fastest because of what we call the proximity effect, because it's right there. It's already right next door to that carbocation, so it can form really quickly. In order to go all the way to the other side of the molecule, it would need more thermal energy in order to do it, right? It would need to travel over to get to this side of the molecule, which requires some heat. All right? So when we're talking about our kinetic product here, our kinetic product is always our 1,2 adduct. And it's always our 1,2 adduct because of what we call the proximity effect. That bromide ion is right next to that carbocation when it forms. Okay? So then what about our thermodynamic product? Why is our thermodynamic product the 1,4 adduct in this case? Why is that the most stable of our possible products here? Well, let's look closely at these two molecules. Why would this one be lower energy than this one? Cash, you're up.
The terminal double bond is less stable than the one that's in the middle.
Yeah, and what do we call this? We call that degree of substitution, right? What's the degree of substitution of this this alkene here? Just a mono substituted. And what's the degree of substitution of this alkene? This is a di substituted. So our 1,4 product is more stable because it has the more substituted double bond. All right? Now, but this is important. That's not always going to be the case. That's the case for 1,3-butadiene, but I can come up with another conjugated diene where that isn't the case. All right? So for the 1,4, for our thermodynamic product, we're going to have to note here that it could be either the 1,2 or the 1,4. We got to know what to look out for here. We want the more stable, aka more substituted alkene product. All right, so the bottom line is for our 1,3-butadiene, our low temperature product is the 1,2, and our high temperature product is the 1,4, but we can't just get married to that like it's a hard, fast rule. All right, it's true that at low temperatures, 1,2 is always going to be your major product because it forms the fastest. All right, but your high temperature product is going to depend on the degree of substitution. Sometimes your 1,2 is more substituted, sometimes your 1,4 is more substituted. You're going to have to draw them both out and establish which one is going to be the lower energy product. Okay? Cool. All right, so we got this temperature control here. Kinetic product is the one that forms at low temperatures. It's the one that forms the fastest because of that lower activation energy. Our thermodynamic product is our high temperature product. It's going to be our more stable product. All right. Now, one more complication that I can throw at us here, and we're going to make a special note. We were working previously with a symmetric diene, meaning it wouldn't have mattered which one of those double bonds I chose. I would have gotten the same intermediate. All right. But what if we deal with an asymmetric diene? All right, so let's just do an example here of an asymmetric diene. All right, so like this guy here. So now we're going to throw a methyl group on there. 2-methyl-1,3-butadiene. Okay, so importantly, proximity effect still rules, right? My proximity logic does not change. So we can say that our kinetic product is still always that 1,2 adduct. Okay, the problem is that I got two possible 1,2 adducts that I can draw using this particular asymmetric diene. So what I want you to do is first we're going to take this pi bond. We're going to add in our HBr at low temperatures. And I want you to draw me our intermediate, our carbocation intermediate, and then the product that we would get from that carbocation intermediate. All right, but then we're also going to do the same thing with this pi bond right here. Looking at what happens when we do our HBr at low temperatures. We'll have a different carbocation intermediate and a different product that would form from that carbocation intermediate. Okay, so if my orange pi bond here, the one on the left, played the role of my nucleophile, I would get a carbocation located right here, always in the allylic position, right? But different than if my green pi bond played the role of the nucleophile, I would get my allylic carbocation over here, and these would lead to two different products. Both of them are 1,2 adducts. All right, so how am I supposed to tell which one is going to form more preferentially than the other one? All right, well, remember, we said that our low temperature product is the product that forms the fastest, meaning it has the lowest activation energy. All right, so always the 1,2 adduct, we need the lowest activation energy. Okay, in my graph here, where's my activation energy in the middle? The left, the right, or the middle? Or again, okay, I gave it away. Where's my activation energy again? Left, right, or middle? In the middle. All right, and what lives here in the middle? the carbocation. All right, and so now there's going to be a difference between my carbocations. Both of them are allylic, so they're both great from that perspective. But one of these is even more stable than the other one because of that degree of substitution of my carbocation. All right, so this one here is my more stable carbocation because it's more substituted. And since my lowest activation energy is what's going to lead to my major product at low temperatures, yes, we want the lowest activation energy, which means we're looking for the more substituted allylic carbocation. All right, so at low temperatures, this 1,2 product would be preferred over the other one because it's got the lowest activation energy barrier. All right, and just to finish this off quickly, I will just note that I did this example in a much more longer, kind of drawn out way, step by step, and that lecture video has been posted. So if this notes here isn't enough, you can go through and watch that kind of in a more step-by-step way. I knew we were going to run out of time here. But just to kind of finish off our notes here, if we have an asymmetric diene and we're looking for our thermodynamic product, like we said, it could be either 1,2 or 1,4, meaning we have to just draw all of our possible products determine which one is more stable based on degree of substitution. All right, so since at high temperatures this thing gets to sample all possibilities, we got to draw all 4 of our possible products that we would get to figure out what is going to be our major product at high temperatures. Cool. All right, we ran 5 minutes over. We're going to start lab 5 minutes late, so we'll start lab at 35 after.